All right, let's get started. Hey, so out of curiosity, how many of you guys attended my session yesterday? All right, cool. So I can zip right through like intro stuff and go straight into DocDB. I assume you guys all know what it is now. So I mean, kind of what we talked about yesterday was, what are the broad categories of problems that NoSQL databases solve? What does the NoSQL landscape kind of look like? How do I kind of think of this and where this space is headed? And when is DocumentDB, when is it a good fit? For today, I'm going to assume you have an idea of when it's a good idea to use it. So I'm going to focus more on, okay, how do I take advantage of this, right? So we're going to talk about things like how do we model our data? How do we look at things like indexing? How do we look at things like geo-replication? And also kind of give you a sneak peek at where DocumentDB is headed next in terms of our roadmap. Sounds like everyone attended my session yesterday, so I'm going to probably just hit next through these. I mean, the broad problems are volume, velocity, variety, right? Volume is I have so much throughput, so much storage, doesn't fit on a single box anymore, I need to scale out. For velocity, this is the problem of, great, I've scaled this out, how do I get low latency access to my data to make sure that I have highly responsive applications? Variety is how do I deal with these schema changes? We see these problems in a variety of scenarios, ranging from retail product catalogs and personalization to gaming and IoT to doing social analytics. The main things that DocumentDB really focuses on from a capability standpoint is elastic scale, guaranteed low latency. When we talk about replication across regions, giving you some sanity around consistency. And then also handling variety schema, especially if you have, let's say, a 5-region deployment. Handling schema changes when you have, let's say, 100 partitions times 5 regions, and now you want to perform an update, and you're told the app can't go down. You need availability. How do you do so? And having things like automatic indexing and having this as a platform as a service makes this really, really easy. So, okay, DocumentDB 101-ish. I'll kind of give you some context on how DocumentDB is built behind the scenes. From a user perspective, what's nice is a lot of this is abstracted away from you. But with that said, it's still very, very good, I think, to understand what's going on behind the scenes, so that way you are able to take advantage of this to the most. So basically our topology, we have built this as a distributed system, and it actually is truly globally distributed across 30 different regions, or however many Azure regions there are. It keeps going up every day. Within each of these regions, we have a set of data centers, and what we have is, we call this a federation. Think of this as a cluster. This federation is spread across about 10 to 20 fault domains, depending on what region, the size of the data center, and how much space they give us. Think of fault domains as a rack. A rack has a shared network connectivity, shared power, and so when you spread a cluster across multiple fault domains, what's nice is you get resiliency against hardware issues. Now within this, we have a set of resources. What you will be storing your data in is a concept called a collection. Each of these collections will have multiple partitions. Each of these partitions will have multiple replicas. So within a data center, what we do is we actually replicate all data 4 ways. This is how we're able to give you 4 nines availability SLA on a single region. And this also gives you, these are spread across these fault domains to bring that resiliency for you, to you. Now, what does this look like from a user perspective? Here's kind of the resource model. As you get started with DocumentDB, the first thing you're going to do is you're going to create a database account. A database account comes with a couple things. It'll have a URI that you can connect to, along with a set of keys. Basically, DocumentDB uses HMAC authentication. Every time you make a request to DocumentDB, it'll use one of these keys to sign the request before shipping it to, over the wire, basically generating a signature. All of that gets shipped over the wire over SSL or TLS 1.2, and the account is the level at which you get these keys. Underneath the account, you have a set of databases. You can think of these as logical entities. And you can also think of collections as a logical grouping of one or more partitions, where a database is a logical grouping of one or more collections. Underneath a database, we also have some features like users and permissions. So if you want to do fine-grained access control to your data, let's say down to an individual record, you can create a permission to, basically it's a tuple of a user and a resource. That resource can go all the way down to a document level. And basically you're going to use a token that's generated from the permission to sign the request rather than the master key belonging to the account. Underneath the collection, this is where things get interesting. This is your actual data, right? Your data is documents. When I talk about documents, I'm not talking about Word documents. I'm not talking about PDF documents. I'm talking about your actual data. These are JSON documents. We have a few other things, including stored procedures, triggers, and user-defined functions. You can think of this as server-side scripting layer for you to run some business logic. This is actually the mechanism that DocumentDB uses to give you transactions over multiple records. The user-defined functions allow you to extend the query language. One little difference, if you're coming from a SQL background, stored procedures are a little bit different in DocumentDB's world. Rather than just writing some T-SQL and representing this as a body of logic, stored procedures are actually optimized around multi-record transactions. And so if you need transactions over multiple records, use stored procedures. If you have a bunch of, let's say, read-only operations, I actually highly advise you to write this in the client-side application. You can think of attachments as a way of attaching media, like blob files, to a record. And like an example scenario for this would be if I have a social media application, let's say I post a photo on a social news site, and I want to tag this photo, let's say with a title, an author, a description, a bunch of metadata, and I want to be able to query over that. The document provides a layer of queryability over this, and then you can attach the media file and have that stream directly back out to the app along with the document. Our partitioning model, basically you can think of it as a collection has multiple partitions. Each of these partitions they'll be replicated 4 ways within a single data center. Now, if you now distribute this across multiple geographic regions, the number of replica sets and replicas you have this gives you a really, really high amount of redundancy. This makes sure that your application is truly resilient. It also gives you a mechanism for basically supplying even more throughput. Now that we have kind of an overview of the resources that you have at your disposal with DocumentDB, let's talk about some of the things that you really should understand to be able to build an application that really takes advantage of all that DocumentDB has to offer. If you take, I think at the end of this talk, like if I were to summarize the whole thing, there's two things I really want you to remember, even if you forget everything else. Number one, collections are not tables. I'll repeat this, collections are not tables. So collections do not enforce schema. In fact, because they have one or more partitions underneath, they are reserving a set of system resources in DocumentDB. You will do yourself a lot of favors in terms of cost by co-locating entities within the same collection. You can do so because they do not enforce schema, and this actually brings a bunch of benefits to you. In terms of mixing entities and co-locating them within a collection, remember, DocumentDB automatically indexes every property of every document. The pattern for this is you simply annotate documents with a type property. So, I mean, what are some of the benefits of co-locating different types in the same collection? Number one, NoSQL databases generally, they do not have the ability to join across documents, join across partitions, right? So how do you actually query back a bunch of different entity types within the same single network request? If you were to co-locate these in the same collection, because queries are scoped to a collection, let's say I have 2 different types of documents. One is a cat document over here, and the other is a person document. So it's me and my cat. If I want to query both of these different types, by issuing a single query. If I have a shared property, let's say family ID, I query on this shared property, I will actually get both of these different types back in the single network request. If I now wanted to take this a step further and say, well, I only want one of these types back in my query, this is actually quite simple, right? You just add a filter on this in your where clause. And the fact that this is automatically indexed means you don't even have to set an index to serve this. In addition to being able to query across multiple entity types within a single network request, you'll also, the other benefits you have to reap by co-locating entities in the same collection include performing multi-record transactions across these multiple types. So the boundary for a transaction is actually going to be a partition key, which you can think of a collection as having multiple partitions. Basically, I'll kind of give you an idea of partitioning actually here in just a second. And of course, cost. Every collection has one or more physical partitions underneath, so you don't want a bunch of these with very, very low utilization. Otherwise, the service cost kind of goes up on you. So with that said, why do I keep bringing about partitioning? This is actually, like, I think the biggest part about modeling your data in DocumentDB. We basically think of the world in two dimensions. One dimension is storage, the other dimension is throughput. That way you don't have to deal with all this crappiness around thinking of the world in terms of hardware, like how many gigabytes of RAM do I need to support 1,000 requests per second? If I tell you tomorrow that your application now needs to double the requests per second, or let's say add another 2,000 writes per second, how much RAM do you buy? How much CPU do you buy? Who knows, right? Like you might do some performance, stress testing to find which bottleneck it is. Once you found the bottleneck, you still don't know how much you add, so you just throw some hardware at the problem and hope things go well. That is not a good model, I think, for thinking about capacity. It makes things very difficult. This is why most Azure services try to abstract and make this easier through a logical abstraction. In fact, if you look at just even one metric, the most important metric for DocumentDB, and I think this is true for every Azure data service, look at the request units, the DTUs, the DWs, but think of request units as a logical currency on top of all of the physical resources it takes to perform a request. This is the amount of CPU, the amount of memory, and then amount of I/O. Each of the replicas in that cluster now gets a fixed budget of RUs that you basically get to provision. You can dial this up and down. As you dial this up and down, if the replica has reached its limit, what we'll do is we'll automatically add more replicas backing that collection. We'll add more partitions behind that collection. The reason why we use request units and not requests, well, it turns out every request costs a different amount of system resources, right? A create request will use a different amount of resources than a read request. For example, because we replicate everything 4 ways, every time you perform a write, we need to actually touch 4 machines. Every time you do a read, depending on consistency level, if this is eventually consistent or session consistency, we can actually pull this from a single replica. And so this actually comes down to how we baseline request units. A read on a 1 kilobyte record typically takes 1 request unit. Well, actually, it just takes 1 request unit for session and eventual consistency. A write typically takes about 5 request units, and this is the cost of indexing plus the cost of putting it on 4 replicas. The model here then is you have a convenient model for you to provision throughput. So instead of thinking of the world of how much gigabytes, how much CPU, how much memory I/O I need, I can think of it as if I know that my requests, let's say I need to do 1,000 writes per second, and each of them costs 5 request units. I do 1,000 times 5, I provision 5,000 request units. Tomorrow, if my app, let's say, gets featured on the iOS App Store and traffic ramps up 100x, great. You actually can just simply either do this calculation again or just increase the RU by 100x. The capacity planning becomes dead simple. This is basically a token bag system. If you exhaust the amount of provisioned throughput, you just get a throttle, you retry. This is actually a very nice way of, if you have a spiky workload, moving that spike over on the retry to kind of even out that workload. Or alternatively, you can provision more request units. But basically, you have this knob available to you. The pricing now, because we use these two-dimension storage is a consumption model. Throughput is a provision model. The reason why we do provision model is we want to give you predictable performance. We've learned a lot from previous services we've built around Azure. If you don't do a provision model, it's very hard to actually guarantee and protect tenants against noisy neighbor problems. Instead, what you want to do is provision this, let people set aside these resources so that they have them on demand. That means if you need, let's say, a million writes per second, you will always have a million writes per second set aside and available to you. So what happens is behind this collection, we will actually transparently back it by a number of partitions. Basically, you can think of it as we'll calculate how many partitions are needed to serve the amount of storage and serve the amount of throughput. And we'll take the max of these two values to make sure that there's no bottleneck in either. If you ramp up throughput tomorrow, what will happen is we'll spin up additional physical partitions underneath the hood. Now, this is actually transparent to you. And what's nice is this way you don't have to do node math. Most people, I think, have a very good understanding of I need, let's say, 1,000 requests per second or 5,000 requests per second. This doesn't translate to how many nodes do I need, right? How many partitions, how many replica sets do I actually need to back this? We allocate a number of partitions. The thing that you need to do as a user, partitioning has almost been completely solved. You almost don't have to think about it. The one thing you do have to think about is giving us a placement hint on how do we distribute that data. You can think of a partition key as a logical thing you set on a collection. Let's say if I have a multi-tenant application, I might partition by the tenant ID. Or if this is an IoT scenario, I might partition on something like a device ID. What we'll do is we basically do hash partitioning on this partition key. We use consistent hashing, and we'll take basically a range of the possible values, the hash values, and we'll divide those across these partitions. So a partition key, all of the data for any given partition key is guaranteed to live on one physical partition. This is why this is the boundary for transactions. But with that said, a physical partition actually might contain multiple partition keys. I'll kind of get into then what do you need to think about. But some things you want to think about is when you choose a partition key, this is also how we're going to, because this is a placement hit on how we place data on writes, this is also what you're going to supply to us on reads to prevent a fan outs. Generally speaking, I mean, the things you're going to want to do is you're going to want to make sure that you don't have any hot partitions, right? If you partition on something, let's say timestamp, and the current time on writes, then at any given time, all of your writes are actually hitting a single partition. That's not a good way. You end up having to, you get bottlenecked by what a single partition can serve. Don't do that. Instead, what you want to make sure is the overall request volume is nicely load balanced across partitions. This is where you'll really want to understand the workload, the nature of your workload. I'll kind of tell you the recipe on how, kind of the steps I think about. You'll also want to make sure that individual queries try to minimize the number of cross-partition lookups. So the SDK is actually intelligent for DocumentDB. It gets shipped with a query parser. And what ends up happening is as long as that partition key is in that where clause, what DocumentDB will do, the client, is it'll minimize the number of fan-outs. So as long as you have that partition key in that where clause, you, generally speaking, are good. However, what you want to do is make sure you try to minimize how much you omit it, because if you omit it, we have to fan out to every partition to look for that data. We basically don't have a hint on which partition we want to look at anymore. Some of the design goals that you'll want to think about when you choose your partition key. I mentioned load balance the overall request volume across a large number of partition keys, as well as trying to make sure that the partition key you choose is represented in your read pattern, so that way you minimize the amount of fan-outs across these partitions. The other thing that I should stress is, I mean, for best practices, you'll want to keep, you basically want high cardinality for these partition keys for whatever you choose. If you tell me that you only have 10 possible values of partition key, then I can create no more than 10 partitions to solve, to serve your throughput. Whereas if you have 1 million partition key values, I might pack them to 10 partitions today to help save on costs, but the moment you ramp up throughput, I can always split those partitions and bring you more throughput. So you basically want to make sure that you choose something that gives you a lot of granularity, that spreads the load across a lot of partition key values. And for any given partition key value, you also want to make sure that you stay, generally speaking, under 1 gigabyte for storage and under 1,000 request units per second. You can go higher, but because we co-locate them on physical partitions, it's still good to try to use this as one of your design goals for your choice of partition key. The other thing is I mentioned store procedures. When you run them to do transactions across records, you actually have to supply the partition key. That's the scope for a transaction. And thus, when you're looking at what partition key you place on that collection, you'll want to make sure that that reflects your transactional needs. So, I mean, the way you now think about the problem, just understand the data access patterns. If you tell me that your application is 90% writes and 10% reads, then I would say, well, it might make sense for you to focus on the 90%, right? Focus on the writes. Don't concern yourself too much on things that are infrequent. If you have occasional fanouts, that's quite okay. Especially for read-heavy applications, but even for write-heavy applications, a good way of looking at candidates for your partition key, just look at your queries. If you find that, if I look at my top 3 queries, or top n queries, if all of them have a filter on a common property, let's say tenant ID, I would basically tell you, if you're on a call with me, maybe you should use tenant ID as your partition key, right? You always filter on it. And that way, your top queries all don't have to fan out. Otherwise, I mean, make sure you avoid hot partitions, aim for high cardinality. More partition key values is always happiness. There's some tricks for how you can increase cardinality. An example is appending a range of time onto a property. So let's say that I know for a given tenant, the volume can grow quite large over time. Well, if it grows quite large over time, I might just do tenant ID plus, let's say, the current month, January, or what is the month right now? Is it February right now? I might do tenant ID plus February, tenant ID plus March, tenant ID plus April. That way, for any given month, I know that this puts a bound on how much data can grow for that given partition key value. This is one way of increasing the cardinality for that. The next thing in terms of data modeling that is good to understand is object model. I will kind of mark a caveat here. For object model, this is where things get a lot more opinionated. For your choice of partition key and your choice of how you distribute data across collections, these are things that you're operating with like very well-known constraints. When you look at object model, you actually have a lot more freedom to kind of choose one design over another. In general, I mean, we basically have built a schema-agnostic database. We allow you to ingest records of arbitrary schema. And this means you can also, because it's JSON, you can denormalize. But just because we let you denormalize doesn't mean you always should. You should still think about how you model this data. So, I mean, the basic approaches, if you're coming from a relational background, you're probably used to just trying to normalize everything. The first thing actually I see a lot of people do is they'll just look at the entities. And right away they'll think about, oh, each type equals, let's say, a table. That is not a good way to just blindly, even in a relational database, you actually shouldn't do this. I think too many people do it. But given an object model, because we accept JSON, you also have the ability to denormalize by having nested object, nested arrays of objects, and can go very deep. You basically now no longer need to normalize and shred basically everything by type, but you can actually represent things just as they are, however the object looks like in the application. So rather than thinking about things in terms of entities and relationships, you can actually compact your data all into a single record. So let's kind of talk about like when you would want to do so, when you would not want to do so. I mean, this is kind of the question of, do you embed this data? Do you reference this data? What are some of the trade-offs to think about? For denormalizing data, at a high level, what you're actually doing is you're optimizing for reads. Basically, you can now do point reads. We don't have to resolve any references. All of this data gets shipped back very cheaply on a point read, right? And this makes sense when you have, here are some of the hints, normally signals that I would guide towards denormalizing, but these are not hard rules. And always remember, these are not hard rules. This works well when a relationship is hierarchical in nature. It works well if you have arrays that the array grows within bounds. The reason why you want to make sure that this array is bounded is because at the end of the day, there's always going to be this thing called a document size limit or a record size limit. If this array can grow to infinity, and it is very likely to do so, at some point you're going to hit a record size limit no matter how much we increase it. And we increase it periodically as we make improvements to the service. But if this thing can grow to infinity, then, I mean, unless a document can grow to infinity, you don't want to keep everything in one document. The other thing to think about is the more records you have, or the more properties you have within a document, the more you have to basically write. When you do a replace on the document, it's going to increase the cost of replaces because the document is high. So you'll want to do this only for when the data changes infrequently. I guess kind of in summary, this is a nice way of optimizing for reads. The problem with denormalizing is, let's say if you have a shared parent, this is actually like a many-to-many relationship. The moment I perform an update on that parent, because it's shared, I now have to fan out that update, right? That's, in general, like, it makes write performance kind of crappy. So if you have a many-to-many relationship, or you have an array that grows without bounds, these are strong signals for you to, well, split these up into separate records. And typically, at a high level, what you're doing here is you're now optimizing for write performance. Because you have many small records, these are very cheap to update. Really, like, you don't want to think about this world in terms of normalizing and denormalizing at a record level. You want to actually think about this at a property level. This is where most people will find happiness. And think about optimizing it for your workload. So rather than starting with an entity and going from there, look at, what are the actual reads and write patterns coming from the application look like. If you have an application that's serving, let's say, a REST API and shipping some JSON back, that might give you some hints on what the JSON in your database should actually look like. You're going to have shared properties. An example is if I have, let's say, a product catalog, I have a product listing page and a product details page. The product details might have a lot of properties I don't need to show in a summary. Those fine-grained details actually might be the things that mutate quite often. And so what I might do is I might actually duplicate things like the title, a short summary and an image in a product listings document. And that way I can pull these things back very cheaply in my application. Another good way of framing this in terms of following the workload is also look at how frequently certain properties change. If you group certain properties that mutate quite frequently together and separate them away from things that don't change as frequently, you've lowered the cost of these updates drastically because you can now update a small record as opposed to a larger record that has a bunch of things that aren't mutating with it. So this is another way of just thinking about this problem. But once again, there's no, like, at least for object modeling, there's no exact science to this. This is all kind of opinionated, but these are some of the things that I tend to look at when I think about it. Sorry, how does that reflect on the container itself?
How does that reflect on the container itself? Yes. How is it actually? So you told me that the container is an aggregation of all the documents. You're separating here for two objects. You just dump
So how this actually gets stored, there's a couple of different things. One, the document gets stored kind of as is. We also build an inverted index on top of the record. Basically, an index is created on each of these different partitions. And the container for all of your documents is, of course, a collection. This is where then thinking about, well, how do I distribute that data across these physical partitions underneath the collection comes into play. And that was the exercise of choosing a partition key. By the way, I do understand that this is a bit of a shift in terms of how you think about modeling your data if you're coming from, let's say, a relational database. If you do need help with this, please do reach out to my team. We're more than willing to help you guide through. If you tell us like an exact scenario on what you're trying to do, we're more than willing to actually help you and just kind of give you an idea of how we would think about the problem. And I find that once you've done it once, it becomes very easy, because every time you do it, it's the same set of rules that you're thinking about. Now that you've gotten an idea of how you model your records, how you distribute your records, how do you actually query this back, and how does indexing work with DocumentDB? So in addition to storing the actual record, we build an inverted index. And the way we do this is, what we do is we represent JSON as a tree. And so basically, if you think about this as a record, this as your documents, what the index will look like is, if we build an inverted index on this, the root object is the root of the documents. The children properties, or child nodes, would be the child properties within the document. And this will go all the way down to the individual value. Now, if we take a couple of these documents and merge these two into a tree, we have our index on the collection, right? And the way you then navigate, let's say I have a query up here where I got two sample documents. Each of them have a set of locations, a headquarter property, and some exports. Let's say I want to project the locations on a document where the headquarter is Belgium. What I'm going to do is I'm going to navigate down this tree. I'm going to find that this holds true for this record, and then I'm going to project that side of the tree so that this is what gets returned from the query layer, right? I'll also kind of just briefly mention we do have a JavaScript query API for those who really like fluent query APIs. We do have a link provider in our .NET SDK, but because we have a server-side programmability layer, like store procedures, triggers, that is written in JavaScript, we actually have a fluent query API that's modeled off of basically ES6 array operators. If you think of an array as a collection and look at all the built-in operators, we can translate those into our query IL and run them efficiently against the database. We also support user-defined functions as part of the query layer. So if we miss something in our built-in functions, you can actually call something like, let's say here I write some JavaScript to do a tax calculation. In the projection, when I pull this back, let's say I filter on revenue, I find that this is the only record that meets this criteria. I can actually then run this against the JavaScript runtime that's hosted within the database and do some mutation on the projection. But the way you can think about the index, I kind of showed like what an individual record would look like on an index entry. Basically, the index in the partition you can think of as we merge each of these, and then the leaf nodes, the inverted index basically now points to, hey, if you are looking for a record whose exports dealer, the first array name is Hans, then this will be document IDs 1 and 2. And so that way we can then return documents 1 and 2. This is basically, we navigate a path, we evaluate the filter, and then this will give us a list of postings. In addition to just using this for range and equality operators, we also do a few things. So there's a few additional things that happens in indexing. One is for wildcard queries. This is for if you don't know the index value. We actually do a special property, special path for arrays. so that if you want to query across all of the array elements without knowing the index, we actually can do so efficiently on the index. And then we also have geospatial support, should you want to do things like distance, polygon, like bounding box queries or anything like that. In general, these are the operators that you'll want to make sure you include on your filters, right? These are the filters that actually take advantage of the index, well, filters and the inclusion of order by. So equality operators, we actually have 3 different modes of indexing. I'll kind of talk about it on this next slide. We have hash, range, and spatial index. Now, hash is very good. You can think of it as doing hash lookups against a path. And so this is very good for equality operators, like first name equals Andrew. Not so good for range operators, like less than or greater than. Whereas if you want to do range queries, you should use a range index. We also support index precision. This is a little out of date. We actually support 3 to 100 bytes for the precision of the index. We also support a dynamic value, -1. -1 is basically the, we basically look at the value and what we either hash to, the number of bytes, or the truncate to for range. We will dynamically allocate based off of the size of the value. So if a value is, let's say, 3 bytes, there's no reason why we need to hash it to 100 bytes. We can actually save space by using a dynamic precision. But these are some of the things that you can toggle on and off, in which you can turn the automatic indexing capabilities on or off at a collection level. You can then define whether you want consistent or lazy indexing. You can think of consistent indexing as every time I perform a write, I will synchronously update the index on my database so that it's immediately available for query. If I do lazy indexing, this is actually for bursty write workloads where you don't need to query for that data back right away. Instead, what happens is you won't pay, in terms of RU, the cost of indexing upfront on writes. This will drastically lower the RU cost of writes. And then as a background task, basically, for any provisioned RU that you have on the collection that is unutilized, that background task will use those to catch up on indexing lazily. You can actually configure what paths get indexed. So that when you think about that tree, not just defining which individual property in that document, but you can actually do things like broadly on a path like so. And so we basically have some operators, like if property path, we have a document that has a prop property. Let's say it has a bunch of properties underneath it. You can actually include things like a wildcard in the path to make sure that you can automatically index everything on that. And I mean, even a pattern for this, if you don't want to ever touch your index policy ever again, is you can create things like indexed properties, unindexed properties, and then do a wildcard on the include for the included paths. By default, what DocumentDB will come out of the box with is range index on all paths for strings and numerics. And we find that this works quite well for a lot of folks who don't want to touch indexing as they build their app early on. But then over time, as you understand the actual workload, what the actual query access patterns are, people will then start tuning it. So you can do kind of an opt-out model for indexing rather than an opt-in model, just to speed up development drastically. With that said on indexing, let's talk a little bit about geo-replication or distributing your data across geographic regions. The partitioning model I mentioned, we have basically a collection that's partitioned that then has basically a set of replicas for each of these partitions, right? Now, each of the replicas you set across geographic regions are actually active, meaning they can serve requests. So if you want to, you can think of this also as if I have a different request volume in different regions, I actually can dial this knob in different regions. This also gives you a high amount of redundancy for your data to make it very resilient. Whenever you're talking about replication, I think a good thing to also think about is consistency. You can think of this as when a client makes a write to, let's say, a primary, what happens to these secondaries? Do they block? Or do we wait for an acknowledgement that that write has propagated before serving reads out of them? Or do they just serve reads? And that way you can get higher availability, lower latency, but they can give stale reads, right? So I mean, this is kind of a hard thing to think about in terms of not a hard thing to think about, but these are kind of hard trade-offs. So if I wait for quorum to be established, I'm going to have very, very high latency. Basically, every time I have a write, I now have a bunch of reads blocking until quorum is established. And for eventual consistency, I just have no sanity around when I perform a read. Sometimes I get the new value, sometimes I get the old value. What the heck is going on with the system, right? This is where we give you a tunable consistency model. You just configure this on the database account level as a default, your default consistency. You can actually then weaken consistency on a per request basis. So if you find that, generally speaking, you want something like bounded staleness, you can then do an override on the request and weaken consistency all the way down to eventual. So that if you have certain requests that really want to make the trade-off where it wants to optimize for latency rather than consistency, well, you can do so on a per request basis. For session consistency, think of this as every time I perform a write, we actually have basically a latch-free append-only structure persisting these writes. One of the things that gets encoded into the session token is basically a log sequence number. So if you now have, let's say, a write from in a session saying, hey, I know that I've written record number 500, basically on a read, when you use that session token back on the read, it'll say, I know I saw write number 500. Any read you give me, that replica should at least reflect that value before serving a value back to me. This means you always get to read your own writes. For bounded staleness, this allows you to define how eventual is eventual. Otherwise, if there's no bounds on this, then what's going on? Like when will this write actually manifest and appear on my reads? You basically can set a bound based off of the number of writes or a time interval. And if either of these limits are hit, we'll actually apply back pressure on the write path to help read replicas to catch up. Those are, I think, the high-level things to think about in terms of DocumentDB. Before I kind of jump into general tips, I'll also kind of just show you a demo on how easy this is to set up. So let's say I want to replicate an account and set to multiple geographic regions. Actually, if you guys have played with SQLDB, it's a pretty similar experience. What I'm going here is this is the Azure portal. This is basically the portal where you're going to manage all of your Azure resources, right? I'm assuming most of you guys have played around with Azure before. But if I want to set up additional regions, if you ever have had to done this with, let's say, on-prem databases, I mean, you know that this is a very, very painful thing. One of the nice things of a fully managed service is, let's say I want to add a region in West India. I actually just click on this on a map and hit save, and it'll just add a region. I think this is really cool. Once you've set up a region, there's a couple things you can do. One is, how do you configure consistency? So while that one is adding a region, I'm going to go to another account of mine that I have. If you go to the settings here, this is where you can define consistency. If you have a single region deployment, will allow you to do strong consistency. But once you replicate across regions, because of the latency of having to travel across geographic regions where the latency is high, you get to choose between bounded staleness session and eventual. Once you have set that and you have your region set up, a few of the other things we allow you to do, because we have quite a few people who actually do multi-region deployments to get low latency for a global application. You can also set failover priorities on, rather than just having us pick a region to fail over. If, let's say, a meteor strikes a data center tomorrow, you can actually define what priority you want to fail over, as well as manually fail over. So if you want to do a BCDR drill, let's say you want to see how resilient is this, you can actually trigger a failover and just kind of watch how the application behaves. So what I've done here is I've actually built a little web app. What it does is it has a globally distributed DocumentDB behind it, set up for 13 different regions. I've also set up a little chart here. This is a little cheat sheet on if I do a ping from, let's say, a VM between Azure regions, what is the round-trip latency between these two regions? If I have a single region application, then what will happen is if I have to make a trip, let's say my data is in East US and I'm making a request from Southeast Australia, I'm looking at 250 millisecond latency at best for that round trip. But by bringing your data to each of these regions, we can actually give you low latency around the world. And so what I've done here is I've replicated my data across 13 regions. And these are all served behind a single multi-homing API, meaning all 13 regions are on the same endpoint. If I trigger a failover, what you'll actually see is the app just stays on. And to kind of give you an idea of what's happening, today we affinitize writes to one region and make reads ubiquitous to all. Notice that I'm getting less than 10 millisecond latency for all my reads in every one of these regions. On the right path, because I'm affinitizing them to a single region, what you see here is as I make live requests from each of these machines, hitting the DocumentDB account in the region closest to it, the writes are still going back to the primary write region, which is in South Central. And so what you find here is these latencies actually reflect pretty close to what ideal numbers would look like from my cheat sheets. To kind of show you like how what happens during a failover, let's say I do a failover from South Central to East US. Whoops. I understand that I am doing a failover. So let's see what happens when I fail over from South Central to East US. What you'll see here is without having to do any kind of redeployment of my application, I can actually define a policy on the client SDK when I establish the connection to the database, what regions that client prefers. And in a minute here, when this actually fails over from South Central to East US, the right region basically will get rehomed to the to East US. And so what you'll see here is without redeploying the app, all the requests now get routed to the right data center. And I think one of the key differentiators here for DocumentDB in terms of geo-replication, one is it's turnkey. It's very easy to set up compared to any other NoSQL database. Two, we also give you a lot of sanity around, you know, when you deal with replication, what does consistency actually look like? So here you can see that my right region is now home to East US because I've failed over to it. Obviously, that means for West US, my latency for writes, I now need to traverse a longer distance, so the latency will go up. Whereas in North Europe, East US is actually closer than South Central, so the latency will go down. But I think what's really cool is I didn't have to redeploy my application at all to be able to take advantage of this. One thing that is kind of interesting, while we built this for doing manual failovers for testing disaster recovery, effectively what this does is this also rehomes what the right region is. We've seen people do kind of a follow the sun model for changing and dynamically at what time of the day where the writes go. So if you have an application that, let's say, you have a global user base, but that user always uses the application from 9 to 5, that means in daytime, when it's the daytime in Australia, it's nighttime in the US, and vice versa. What you can do is you can actually home the writes to, let's say, Australia when it's daytime over here, and then rehome the writes to North America when it's daytime over there and it's nighttime over here. So I think this is actually a pretty cool capability. And, oh, sure. Yes, you can choose which region you access manually. The SDK on the connection policy, you can set a list of regions it prefers so that if one region were to go down, it can actually automatically fall back to something that's different from the priority list on the account level. The account level is actually what will apply globally, but you basically can do overrides on the clients. Can you do it by partition key? That is actually the vision. Yes. So basically, like let's say you have a multi-tenant application where tenants are home to different regions, right? Today, we actually do have some well-established patterns on how you would implement this. Basically, you would wrap accounts home to different regions and partition the tenants across these accounts under a shared data access layer. That's kind of the short summary. But this is actually something that, rather than having to apply this pattern around, this is actually kind of the direction we're headed for global distribution. Because we basically have different partitions, replica sets broken up on this distributed system. There's no reason why by partition key we can home these to different regions, right? And so the direction we are headed on our roadmap is basically allowing you to home by partition key. Let's say it's a multi-tenant app. You can home tenants, affinitize tenants to where they are located, and then make their reads ubiquitous to every region. In terms of other general kind of tips as you play around with DocumentDB, number one, I've seen a lot of folks, what they'll do is I've seen a bad pattern where people will kind of create a new client every time they create a request. The client is actually both thread safe as well as fairly heavy. There's a lot of smart logic included in that. You should definitely make sure that you use a singleton within your application on this. And basically what happens when the client initializes is it's going to get a map of where all the different regions are to be able to do regional failovers. It'll pull that topology, as well as it'll, if you use direct mode, you can think of a topology as we have all of these partitions with all of these different replicas, right? In front of it, for things like a REST API, we actually have a gateway. And so by default, if you connect from gateway mode from an application, it's going to go to this gateway, and then that request will get routed to a replica. The client is also able to do direct connectivity directly to one of these replicas. What happens is when the client warms up, it'll ask the gateway, hey, what are the physical addresses for all of the replicas? And then from there on, all subsequent requests will touch the replica directly, minimizing, basically shaving off a network hop, and that'll shave off like 1 to 2 milliseconds. Because it has this warm-up, if you're doing any kind of performance benchmarking, I've noticed some people will also see this pattern where the first request, when they initialize a client, has really high latency, and then from there on, everything else has low latency. What's actually happening is it's doing that warm-up to pull that map. If you do a .open async on the client, it'll actually basically do all of this warm-up. And so if you're doing any perf testing, it's best to warm this up like so. And the client is also smart enough. What happens behind the scenes for replicas, if a replica were to go down, DocumentDB will actually rebuild and bootstrap another replica. What happens is for the request, when it sees this request, we basically follow HTTP status codes. If you're ever wondering like what went wrong on an exception, if you actually just look at over the status code, we map them to HTTP status codes. So 410 is HTTP gone. If the client sees it gone, what it'll do is it'll ask the gateway again for what is the new mapping and where did when DocumentDB rebuilt the replica somewhere else, what is the address for that? But take advantage of the direct connectivity mode. It defaults to gateway for the reason that if we use our direct connectivity modes, sometimes this doesn't work well with corporate firewalls. But standard HTTP requests always do go through standard corporate firewalls, or most corporate firewalls will allow you to browse websites. So we default to gateway, but where possible, your applications really should be using direct connectivity mode when possible. You'll achieve lower latency if you do so. The other things to think about, consistency levels not just affect latency and consistency, they also affect throughput. Basically, this is because every time when we do things like reads, do we need to get a quorum read, or do we need to read from, we can just take a read from any replica and go with it. And so for eventual and session consistency, you'll get much better throughput characteristics than if you go with strong or bounded staleness. We do have a few interesting features. We've seen people use DocumentDB in kind of event store scenarios. For these kind of scenarios, we actually have a change feed API that allows you to basically get a continuous feed of updated records or newly written records, rather than pulling the database and getting the entire feed. If you have this kind of pattern, use the change feed API. You'll get, once again, better throughput characteristics if you do so. We have seen folks also use DocumentDB as a high-performance key value store, basically using the predictable performance, the partitioning model, all of the different aspects, global distribution, taking advantage of DocumentDB as a key value store. If you decide to do so, you'll actually benefit a lot from, for indexing modes, not only do we support consistent lazy, we actually can give you the ability to turn it off. If you turn off indexing, this effectively goes from a document store to a key value store. I guess one more thing I think I wanted to cover. We also have a feature called time to live. This is basically to set data retention policy. So if you have, let's say, an IoT scenario and you only want to keep sensor data for the last, let's say, 30 days or 60 days, the time to live feature, basically, you can configure how many seconds records will live after their last write before they automatically get pruned. So rather than manually issuing deletes or doing this on a scheduled job, if you use the TTL, this will actually happen as a background task in terms of pruning. And this way, you don't have to use your RU budget for cleaning up data. Instead, what happens is DocumentDB will automatically do so for you. And even though it does it as a background task, it'll actually take effectively immediate for you when the document expires, because what DocumentDB will do is also on the read path, it'll filter out anything that is marked for deletion. So the question is, TTL, is that on the collection level, or what can you configure it on? You can actually configure it both on a collection level and a document level. And if you set it on both, the document level will override the collection level. We also allow you to just completely turn off TTL. So if you have set, let's say, a bunch of TTL on documents, and then let's say you notice there's an anomaly and you want to quickly make sure that nothing gets pruned from there on, if you just turn off TTL, then DocumentDB will basically not respect the TTL values in the document itself, allowing you to basically go, oh crap, turn this off. In terms of our roadmap, where DocumentDB is headed next, I figure this is also kind of fun thing to share so you can see where the service is going. We are working on a Spark connector right now, and this way you can get kind of nice scale-out compute on top of a nice scale-out database. We're actually trying to make this a fairly smart connector. What it'll do is it'll leverage direct connectivity mode. And so what happens is when the connector distributes the compute across different Spark worker nodes, we can actually establish then direct connection from the Spark worker node to the DocumentDB replica to kind of just make sure that this is optimally connected. The topology makes sense. The other thing that we're working on also to make perf really nice for the Spark connector is push-down predicates. For some reason, I thought this was Spark. Oh, we also have change feed. Let me talk about change feed first, and then I'll go on about Spark. For change feed, I mentioned that right now we have the ability to get a list of all of the newly written writes and updates on the collection level. Where we're headed with this is today it doesn't pick up deletes. So the next few things you'll see on the roadmap, kind of like in a crawl, walk, run model where we keep iterating on this feature, is we'll generate temporary tombstones. So you don't have to do soft deletes. You can actually then do hard deletes and pick them up on a change feed. The other thing is because we have a very rich indexing layer, today we just give you a dump of all of the creates and updates coming into the collection. Rather than doing that, we'll also allow you to apply filters using the indexing layer on the change feed. So you can expect this is where change feed is headed next. We are building aggregation into the database itself. There are some caveats to this, but basically you can think of this as performing basic aggregates like sum, average, min, max, counts with a where clause. There's no group by, but what's nice about this is if you want to do a simple thing like find me, all records or how many records have a property that is, let's say is active is true. You can get a low latency aggregation from DocumentDB. This will actually work. The SDK is smart enough to do this across partitions on the client itself. So you can do aggregations across a very large data set, basic aggregates. But for more complex aggregates, for things that involve heavy compute, this actually acts as a really, really nice building block for the Spark connector. And so you can think of it as when you write some Spark SQL, the push-down predicates, not only is it able to use DocumentDB indexing to narrow the data set over than if you were to run Spark over something, let's say, like a blob store. When you do it on blob store, there's no indexing layer, right? So you basically have to munch through all of this data to run that compute job. By being able to push down predicates and leverage the database indexes, we can narrow down the amount of data pulled back into Spark, greatly speeding up your Spark job. On top of that, this also will take advantage of the aggregations that we allow you to do within the database. So if you want to do some more fancier heavy compute aggregates, this is a nice building block to speed up that Spark job. We are also doing some pricing and scaling improvements. In fact, if you look at our service updates, about a week ago, we just lowered the entry cost of partition collections by like 75%. On top of this, we've also found that a lot of people are still, because it's a provision throughput model, if you have a spiky workload, they tend to provision for the peak. Another way that we're going to make DocumentDB cheaper for our users is allow bursting. And so what you can think of this as, rather than having to just get an RU budget per second, we'll also give you a secondary budget of RUs per minute that are slightly lower priority RUs in terms of how the cluster does resource governance. So think of these as best effort RUs, but then it allows you to basically provision below your spike. And then if you do spike above, rather than getting a throttle, we have a secondary budget for you to use, to burst. And this will also basically lower the total cost of ownership for DocumentDB. With this, we've been testing. Before, we used to have these models, S1, S2, S3. S1 came with 250 RUs, S2 came with 1,000 RUs, and S3 came with 2,500 RUs. What we found was a lot of folks needed basically something in between, let's say 1,200 RUs. And so the jump from S2 to S3 was a pretty large jump. Rather than going through this model, we now have basically you provision RUs on 100 RU per second increments. We found that this has been working. We actually launched this about a year ago, and we found that this is, everyone has been flocking to this. There's very few people now using S1, S2, S3. And so the future of this is we're actually going to deprecate S1, S2, S3, and purely rely on this, however much throughput you want to provision, just go for it. This gives you a much finer granularity in terms of what you reserve. We're also working on graph APIs. The future of DocumentDB is this is going to be our NoSQL platform. Basically, we believe we have built a very, very strong set of infrastructure for NoSQL workloads. And we're going to basically build additional APIs to serve different kind of data models. If you want to do graph support, basically we're making a bet on the Gremlin and Tinkerpop APIs. You can think of, if you haven't played with these before, you can think of Gremlin as a query language and Tinkerpop as a protocol similar to, let's say, ODBC. But you can then be able to just write standard Gremlin queries on any kind of Tinkerpop client connected to DocumentDB and leverage all of the latency, scale, and global distribution characteristics on this NoSQL platform. Hopefully, that gives you a nice summary of now when you go build your app, you have a very concrete idea of how you do so. With that said, I do want to get an idea of, are there any questions? I'd love to help. Yes? What is the impact of TTL to indexing? There actually are no impacts to it. What happens is on the read path, if the background job hasn't pruned the record, we actually filter it out on the read path. So from your perspective, from a user perspective, those documents just aren't there anymore. You won't actually get hey, this should have been deleted. And then as the background task catches up and actually cleans up and prunes this, then, those are unused RUs. So it actually doesn't impact your any of the perf on writing to the index. Any other questions? OK. I'm going to chill out right here. And if you guys want to, if you have stuff that's a little bit more discreet, let's say it's something specific to you I want to share, please come up and talk to me. Otherwise, if you have questions for later on, I do have, fill out your evaluations. You should do that. If you ever do have a question and after this, let's say tomorrow you're building and you want to ask, send us an email. We're very responsive. You can reach us at ask.db@microsoft.com. Should be a .com on that. If you want to track service updates as we roll the things I mentioned on our roadmap out, we're pretty active on Twitter. We tend to post a lot of our updates through there, so do follow us. Otherwise, we like to engage on Stack Overflow quite heavily. If you have a question that can be shared publicly, we do encourage you to help us build a knowledge base for everyone, as opposed to just answering you directly. So if possible, do also try to engage us on Stack Overflow. Otherwise, if you want to find more information, you can find more info on DocumentDB at documentdb.com. Thank you.